So in this lecture, we will be talking about electrical properties of colloids. To understand the electrical properties of colloids, it helps us to think of them as tiny magnets because they carry charges, they interact with their environment, and their interaction is very specific, very predictable. So if we take, suppose here as an example, we are taking silver nitrate as an electrolyte, and when we put silver nitrate in a silver nitrate colloid, note that both silver nitrate is here silver nitrate here is both a colloid and also an electrolyte. So let's suppose in the solution there is the nitrate, we have this silver particle, and the silver particle will attract the ion. It could be either positive or negative. So you can see that here we have got a positive side and we've got a negative side. So either the positive side will surround the silver ion or the negative side will surround the silver ion. What happens in both cases is that due to having the same charges as layer, they both repulse each other. Thus, they never suspend and they remain colloid. I hope you got the idea. This is very, very basic. We have studied it before. It's due to the repulsion of having the ion of same charge, and that's why the same charges repulses each other. That's how they never settle. They never create suspension, and that's how they remain colloid. So that was the idea here, and in the example we can see that as the silver particle gets all the positive ion around him, the solution is remained with the negative ions. That's why the dispersion medium is negative and the dispersed phase is positive, because the positive ion are surrounding the silver ion. So that's how there is an attraction between the dispersion medium and the dispersed phase. And if we go to the next chapter, we all know that this colloidal solution is divided into two parts. There is dispersed phase, dispersion medium, and we also know why dispersed phase is negative and dispersed medium is positive. In this case, the dispersed phase is negative because when we put potassium hydroxide, which potassium is the positive and the hydroxyl is the negative ion, the hydroxyl ion surrounds the silver ion. So the silver ion is surrounded by all the negative ions. That's why they repulse each other, and the solution is remained with all the positive ions remaining, which is the potassium ion. You can see them roaming in the solution. That's why the dispersion medium is positive and the dispersed phase is negative. And where we can see that all particles in a given dispersion carry same charges. They carry the same charges. All the particles, all silver ion will either carry all positive charges or all negative charges. So the particles repel each other and do not come close together to form large particles that will precipitate out. So in this case, the precipitation doesn't happen because all the particles have the same ions. And remember very, very closely that same ions repulses each other. So this is the main reason behind the stability we get in obviously the colloidal solution. Here is another example where we are having a silver nitrate colloidal solution, and electrolyte is sodium iodide. And when we put excess sodium iodide, when we put it, so the iodine surrounds the silver. Let's explain it from the beginning. When you take this mixture together, we can see there is silver iodide, which is a colloidal solution, and The other ions that will be roaming in the solution are the left ones, just as like the sodium ion and the nitrate ion. And the silver iodide will take iodine as its surrounding, because you can say that sodium iodide is being put in an excess amount, so the excess amount of iodine remains and they take places around the silver iodide, which is a colloidal solution, and they create the layer, and the layer is negative. We can see that iodine is negative, and that's why the dispersed phase is negative, and the dispersion medium is left with the remaining sodium plus ion, which is why the dispersion medium is here a positive ion. And one of the basic questions that you could ask me here is that why the sodium iodide got a layer of iodine only? Why they got a negative layer? They could also take in sodium plus as their layer. Well, this is where we explain it as preferential absorption. Preferential absorption is a thing where an ion prefers to absorb a particular ion. In this case, the silver iodide prefers this iodide ion, and we all know from where this preference comes. It's due to the common ion effect. You can see that in the colloidal solution there is already an ion. That's why it takes iodine as the layer. It is due to the common ion effect. I hope you studied it properly. I've told you the basic reason here, and after that there is another example which is pretty similar. I hope you'd understand it by your own. So, giving answer to your previous question, we have come to the preferential absorption here. Preferential absorption is where the ion chooses where the colloidal solution chooses which ion to take as a layer. In a lot of cases it takes iodine, the negative one. In a lot of cases it takes the positive one. But the question is, on which basis do they choose these ions? And the answer to it, as I've said before, is common ion. You can see that the iodine is present here. It's also in the colloidal solution. That's why it creates a negative ion surrounding it. That's basically the core idea of preferential absorption. And the next thing is the electrical double layer, which is the main electrical property of a colloidal solution. Let me take a different color. Colloidal, if I give you a little bit of description around it, colloidal particles acquire their charge through selective absorption or preferential absorption. For example, if silver nitrate is given into a sodium iodide, the silver iodide will be produced as a colloid, and it will only take iodine as its layer. I hope you understand. To absorb iodine as its layer, you can see from the picture that it is taking iodine as its layer due to having common ion. So then again, the iodine around the layer, as it is negative, it tries to attract the positive, which is sodium here. Thus again, the sodium surrounds the colloidal layer, and it also creates a second layer. This is known as the electrical double layer. Here the outer layer is known as slippery layer, and the inner layer which is fixed is known as fixed layer. It is also, sorry for the inconvenience, it is also known as the stem layer, and it is known as the diffuse layer. The stem layer is a rigid layer of ions stuck to the particle surface, and the diffuse layer is a cloud of ions that are less tightly bound, can move around freely. That's why it is a non-permanent optional layer. So this was the electrical double layer, which is the first property, electrical double layer. And here is another example. I hope you would understand it. If you do not understand it, by the way, you can comment down below. And the important topics is that, okay, if I say it again, here the sodium iodide will take silver as its layer because it is common ion, and again the silver, due to having positive charges, will attract nitrate and it will create another slippery layer which is known as diffuse layer. The first layer will decide the charge on the colloidal particle, and the first layer will be chosen by preferential absorption or common ion absorption. We have seen before that if you take a colloidal particle, this is a colloidal particle, let's suppose it's sodium iodide. It has two layers. We have seen why it gets two layers. What happens is that due to having positive and negative layer, one layer is positive, by the way, and another is negative, it creates a potential which is known as zeta potential. The positive layer here is strong, the negative layer is sleeping plane, but the diffuse layer is loosely attached, and it creates a potential energy inside them which is known as zeta potential. We have previously studied in our physics about electrical potential, where the positive side and the negative side of two electrodes create electrical potential. These are some positively charged colloidal solution, and this is some negatively charged colloidal solution. The important ones are highlighted here. So, and after that we have the zeta potential. If I try to collaborate the zeta potential, zeta potential is the measured charge of the particle as it moves through the liquid. It isn't the charge at the actual surface, but the charge at the slipping plane. Here is the slipping plane, and the boundary where the liquid starts to move independently of the particle. Well, slipping plane is a plane where beyond that the ions can move independently. Zeta potential is also known as a stability threshold. Generally, a zeta potential is either greater than 30 millivolt or less than minus 30 millivolt, and it is physically considered to be stable. An isoelectric point, this is the pH level where the zeta potential is exactly zero. Isoelectric point is a point where zeta potential is absolutely zero, and at this point the colloids is at its most unstable and will likely come together and create precipitate or coagulate together and will destroy the colloidal solution. Up next we have, I think we have studied the preferential absorption. It is the ability of the colloidal particles to absorb the ions of the electrolyte on their surface, and it is responsible for the presence of charges on the particles. And I hope you study them by yourself. And the next thing is that the positively charged creates a negative electrode, and the negatively charged goes to the positive electrode. We all know that the negative goes to the positive electrode and the positive goes to the negative electrode. They create an electric field, and it's divided into two terms. One of them is electrophoresis and another one is electroosmosis. What happens in electrophoresis is that the dispersed phase in the colloid migrates, and in electroosmosis the dispersion medium migrates. If I try to give you an idea of the electrophoresis, this property proves that colloidal particles are charged. When you place them in a colloidal, when you place a colloidal solution in a U-tube electrolyte, where one of them is positive and another one is negative, what happens is that the positive ion in the solution will go to the negative side, and the negative ion in the solution will go to the positive side. And this proves that the colloidal particles are charged, because if they are not charged, they will not move on the basis of the electric field that we get from the electrolytes. This is the visual of how it happens. And after that, if I tell you what is the utility of electrophoresis, this is how as I've said before, this is how we determine the sign of the charge on a particle. And the modern use of electrophoresis could be, you might be curious to know, and it could be in DNA fingerprinting. Electrophoresis is used to move DNA fragments which are negatively charged through a gel. Smaller fragments move faster than the larger ones, creating the distinct barcode pattern. Well, this was an additional information. And the up next is electroosmosis. Before getting into that, let me show you a visualization of that. Here you can see that it is a negative part, this is the positive part. And in a colloidal solution, some parts are positive and some parts are negative. From where we can know which parts are positive and negative, we have given you a chart where you can understand which colloidal solution are positively charged and which colloidal solution are negatively charged. So you can understand it from there. So what we have to do here is that as the electrophoresis moves on, it attracts, if the colloidal particle is, suppose it is negative, it goes towards the positive side. Thus the water goes to other side of the electrode, and that's how we can understand. If it goes to the positive side, we'll assume that the colloidal solution is in itself negative, and if it goes to the negative side, the vice versa can also be assumed. That's how we understand how a colloidal particle is charged through electrophoresis. And the up next and the last, not the last obviously, the second last property of electrical property of a colloid is the electroosmosis. Well, I hope the video has gotten too long. I think this will be explained in the next video. So this was it. I'm a little bit ill, that's why the classes are taking too much to come out. So I hope, and a lot of understanding might not be very clear as I'm a beginner, so I hope to have your respectable feedbacks, and till then, it's a goodbye.